All right. So we're going to start here with a little bit of like review, mostly because the main ideas from chapter 7 here are an extension of things that you would have done in your geometry course and first semester. So it's been a little bit of time. So I want to make sure that we go back in time a little bit and refresh kind of the starting point and talk about like why exactly what we're doing now is an extension. Everybody cool? Okay. So one of the main ideas that we're going to be looking at in chapter 7 is this notion of solving a triangle. And this is something that we've done in our geometry class, specific to right triangles. So when we talk about solving a triangle, it means figuring out all the missing angle measures and side lengths. So if we think back to our geometry class and think about this in the context of a right triangle, what are some of the tools that we can use to solve a right triangle, to figure out side lengths or angle measures? Yes, Jackson. Pythagorean. Yeah, the Pythagorean Theorem. Very good. Drake, is that a hand?
Yeah. All triangles amount to their degrees will always add up to 1 left.
Good, yeah. The sum of the interior degree or interior angles is 180 degrees. I'm going to put that as the third bullet point. And that would be the other one that I was looking for, yeah. And remember that SOHCAHTOA is an acronym, right? It's just the right triangle definitions for sine, cosine, and tangent. So these two are for right triangles only. This one we can use for any triangles, right? So there's kind of two different situations that we can run into when solving a right triangle. So one situation is where we know like one angle measure and one side length. So here, if I want to solve this right triangle, I need to figure out angle B, side BC, and then side AB. Everybody good to hear, Drake?
No, I'm just wondering, or thinking that this could be used as the next step, but since it's a right triangle, even if you didn't have that 48, you still already have a given angle. The angle side C.
Yeah, so angle C is already 90 degrees. And notice I didn't list that because it's already kind of a given, right? So we already know angle C is 90 degrees, absolutely.
I guess the use of the interior angles.
Yeah, so you're trying to say that let's find angle B first. Yeah. Sure. It doesn't matter which one of these Yeah, it doesn't really matter which one of the three we want to attack first. We can do it in any order, but certainly angle B is the easiest one to find first. So let's go ahead and do that. So we know that angle B is going to be, or we know that the sum of the interior angles is 180 degrees, and we know two of the three. So angle B just has to be 42 degrees, right? Everybody cool there? No big deal. Okay. Now let's say we want to, again, it doesn't matter the order that we do this. Let's find BC next. Okay. So to figure out BC, we want to start by deciding which one of the angles we're going to use. You cannot use a right angle, but you could use 48 or 42. It doesn't matter which one, but you need to pick one and stick with it. Let's just say for the sake of argument, we pick 48. So relative to 48, the side AC that's length is 10, the one that we know, is that opposite, adjacent, or hypotenuse? Good. And the side BC, the one that we're looking for, is that opposite, adjacent, or hypotenuse? Opposite. So which trig function should I be using here? Okay, good. So I know that tangent of 48 is equal to opposite over adjacent. So to solve for BC, I can just multiply both sides by 10. And then it's calculator time, right? When I go fire my calculator up, what should I check before I start typing stuff in? The mode. What should my mode be in? Degrees. How did I know that? The angles were given to me in degrees in the problem. Very good. So I'll just do 10 times tan 48. And I get 11.11. Yeah. We feel good there? Okay. How do you want to find AB? There's really two good ways to do this, Paul. One of them is the Pythagorean Theorem. So what equation would I write to find AB then?
A squared plus B squared.
So what
Using angles, not AB. Sorry, I meant
let's put,
angle line A.
how about you put the numbers in
Okay.
to what you want? So just tell me like what squared plus what squared equals what squared.
I want 11.11 squared.
Okay.
And then plus 10 squared plus, or no, equals C squared.
Okay, well, we'll call this AB is what we had called it before. The thing to keep in mind here, though, is that when we write the Pythagorean theorem, the hypotenuse is always the piece that's by itself, right? Sometimes you'll be solving for the hypotenuse. Sometimes you might be solving for a leg. Really important you're putting the numbers in the right spots in that formula, though. I know you're like, dude, that's trivially easy, but people make that mistake all the time. It happens. So to get AB by itself, we square root both sides. A couple of things to note here. So 11.11 squared plus 10 squared is not equal to 21.11 squared. You can't add them and keep the squareds. You're violating the order of operations. You have to do the exponent before you do the addition. Second common, well, I don't know about common, but and a second possible mistake is that the square root of 11.11 squared plus 10 squared is not 11.11 plus 10. We cannot distribute a square root. So to do this, we're just typing it in exactly as it looks on our sheet of paper. I'm going to use that ands command so I don't have to type all the decimals. Oops. So I get about 1494. So that's one way you could have done that using the Pythagorean theorem. What's the other way that we could have done? Great. I could use the SOHCAHTOA here. So again, if we're using the 48-degree angle, we know the adjacent side, and we're looking for the hypotenuse. So yes, cosine of 48 equals adjacent over hypotenuse. So to solve for that AB, first thing we'd want to do is get it out of the denominator. So multiply both sides by AB. And then divide by cosine 48. And then it's calculator time, and you'll note that you get the same thing. Let's do it this way. Provided that you kept all the decimals like I did on the first computation, but you'll get the exact same number if you keep all the decimals. Everybody happy there? And again, the order in which you do this problem, whether you want to find AB first or BC first or angle B first, it doesn't matter. You don't really need the information from one of these to find another one. So, I mean, you certainly can use it, right? Like when we used the Pythagorean Theorem, we used our answer for the previous problem to do that. But you could have just as easily used cosine and not needed the previous answer at all. So everybody cool there? So that's what it looks like if you're given an angle measure and a side length in your right triangle. Let's look at another situation where instead we're just given two side lengths. Again, doesn't matter the order which you do this. You can do it in any order. The arithmetic might change a little bit, but like you get the same answers. You can do any order. Doesn't matter. I think finding BC is the easiest thing to start with. How would we find BC? Great. So what equation would I write?
You would write b squared plus 12 squared equals 18 squared.
Okay. Everybody agree with that? Again, remember that the hypotenuse has to be the piece by itself in the Pythagorean theorem. So subtracting 12 squared and then square rooting both sides. Again, you could find the number, like find the intermediate step of what 18 squared minus 12 squared is if you want to. I'm just going to type it all into my calculator in just one line, because I think it's easier that way. So I get 1342. Everybody okay there? Okay. So again, let's solve for angle B or angle A. It doesn't matter which one. Let's just choose one. Let's say we pick angle B. Okay. Relative to angle B, we're going to use the sides 12 and 18 because those are our two known sides. Relative to angle B, 12 is opposite, adjacent, or hypotenuse. Opposite. And the 18 is hypotenuse. So I should be using sine so I know sine of B is equal to 12 over 18. And now we want to get the B by itself, so we got to get that sine out of there. How do I get rid of sine? No, it's not dividing. That would be like, I'm going to cancel out this square root symbol by dividing by a square root symbol. Like, yeah, we're going to use inverse sine. So I'm going to take the inverse sine of both sides, and even though there's a parenthesis there when I'm doing that, what I'm doing is not multiplying. I know that it looks like multiplication, and I know what you mean, but So the sine inverse cancels the sine. So into my calculator, I'm going to do sine inverse of 12 over 18. Remember, when we do the sine inverse of something, what do we get back? Angle measures, right? All of our inverses give us an angle measure back. So it makes sense then that to solve for b, we need to use an inverse trig function at some point, right? So my answer there is 4181. And then angle A is easy, right? How am I going to do that? You can do that, Mackenzie. I would do instead, Paul.
You could add angle B plus 90 and then subtract by 180.
Yeah.
That's the right triangle.
Yeah. Well, any triangle has, but yes, because we already know that angle C is 90 degrees. Yes. So Mackenzie, you could certainly do what you're just describing, not incorrect. It will definitely work. I would do this just because the arithmetic is really trivial. Much less of a chance of me making a mistake. So 4819 is my answer there. Everybody feel okay here doing these, guys? Again, this is something you would have done in your geometry class and still concepts that we talked about first semester, but, you know, it's been a little bit. I do want to point out something real quick as a check-ish. It's not a foolproof check, but it's a good check nonetheless. If you remember from geometry, one of the theorems that we had there is that the side lengths and angle measures for our triangles are proportional. That means that the biggest side should be opposite the biggest angle, which is the case that we have here. The next biggest side should be opposite the next biggest angle. And then the smallest side should be opposite the smallest angle, which is exactly what we're seeing here, right? Now, that's not foolproof. Just because that relationship holds doesn't guarantee your answer is correct. But if that relationship is violated, it does guarantee that your answer is wrong. So it's a good check-ish. I should call it a check-ish because you can just look at it really quick and you're like, well, I know it's not blatantly wrong, you know, but if you like wrote this as 4118 or something, it wouldn't be able to catch something like that. If you just transpose two digits when you wrote it down. Can't catch something like that, but if you do something like bonkers, it'll catch that, you know. Okay. Everybody happy? So far, so good? Again, this shouldn't have been too bad, right? This was a lot of review idea. So what you should be left with then is, okay, what about non-right triangles? Right? So we don't have any Pythagorean theorem. That doesn't hold. And we have no SOHCAHTOA. Those are for right triangles only. Oh no! What do we do? Well, we're going to answer this in chapter 7. So in chapter 7, we're going to introduce you guys to two tools that we can use for any triangles. So the first tool we're going to look at is called the law of sines. I abbreviate that just as LOS for law of sines. And what the law of sines says is if I have some non-right triangle, or just really any triangle, whether it's right or non-right, if it's a right triangle, it still works. It's kind of trivial. It's easier to use SOHCAHTOA. What's up?
Is the word you're looking for redundant?
Yeah, I guess, sure. So when we're naming our triangles here, the naming here kind of matters. Okay, so we're going to name these triangles, the angles and the side lengths in a very specific way. So the angle measures, I can name whatever I want, right? I'm just going to name these ABC with capital ABC. The sides then, so the side that's opposite angle A, I'm going to name little a. The side that's opposite angle B, I'm going to name little b. And the side that's opposite angle C, I'm going to name little c. Everybody's okay with that? Now, the letters that you use don't really matter, but the side opposite that angle needs to be named with the lowercase version of whatever letter you used. If you do not do that, these formulas that we're going to give you will not work. Okay? Everybody's cool on how we're naming these? Because if you screw this up, everything gets messed up. Okay? Just to be clear. All right. So what the law of sine says is that sine A over A is equal to sine B over B, and that's also equal to sine C over C.
So what it's saying is that like the lengths or like the ratios for like each length and angle is like shared between all triangles. It's like the same. Is that what it's saying?
Yeah, the ratio of sine of an angle and its opposite side is constant. Right? That ratio is gonna be the same in all those three cases. Now keep in mind with the transitive property, you can set like any pair of these ratios together equal, right? Since all three of these things are equal to each other, you can do like sine A over A equals sine C over C. You guys get that? Right? That it's just a big loop. So why is this true? Like where does this formula come from? Well, this is how we come up with this. I'm going to just take some or pick one of these angles, say angle B, and I'm just going to draw in a perpendicular from angle B to the opposite side. And I'm going to call that side H. So that forms a right triangle here that I've drawn in the blue. So I can say, okay, sine of A is equal to opposite over hypotenuse. I also create a right triangle here on this side in green. If I do the same thing, I can say sine C is equal to opposite over hypotenuse. Everybody's okay with that? Notice both of these two equations contain an H. So if I solve each equation for H, so I multiplied the first equation, both sides, by C, and I multiply the second equation on both sides by A. I can then just set these equal to each other. Since they're both equal to H. Everybody's good with that? And if I divide both sides by AC, I have one part of that equation, right? To get the other part, I just draw a different bisect or perpendicular and repeat the same process to get another pair, and then I can transitive property it all together. I'm not going to do that other half of it because it's the exact same thing we just did. Again, you guys get the idea at that point. So this was like what we did here was like the derivation for this formula. Is that something I'd ever ask you to repeat? No. Is it just something like neat to do or good to see that like I'm not just making this stuff up and saying, hey, take my word for it? Yeah. Okay. So that's one tool that we have. The other tool is called the law of cosines. And there's kind of three different versions of the law of cosines. Now keep in mind that really this is all the same formula 3 times over, right? If I just make a substitution like say, oh, let's let A equal B, then you just get the first equation turns in the second equation, right? Or if I say then, oh, well, let's let A equal C, then I just get this first equation becomes the third equation, right? It's the same thing, just with like a letter substitution. Everybody's okay with that? The way that I kind of remember this is if I'm looking for side A, I'm going to use angle A in the cosine, and then the other two sides make up all the rest of the formula, right? That's the way I kind of think about it. Okay, so we have these two new tools, law of sines and law of cosines. I think the next appropriate question is, okay, great. How do I know which one to use? Before, when it was a right triangle, it was really obvious whether I should use SOHCAHTOA or the Pythagorean Theorem, like super straightforward, right? Here, it's maybe a little bit less obvious in what situations would I want to use one versus the other. So let's talk about that for a moment. So I want you to do that, I want to go back and think about another idea from geometry. I know it was a long time ago. But in geometry, one of the things you spent a lot of time with when you talked about triangles was these ideas of congruence and similarity. Remember triangle congruence and triangle similarity theorems? There's a whole bunch of theorems for these, right? And they're all kind of abbreviated with these letter combinations, like angle, angle, side, or angle, side, angle, and all this stuff, right? You guys kind of remember those? Those are the same way we're going to differentiate it between what situations I'd want to use the law of sines or the law of cosines on. So the law of cosines, again, I would abbreviate this as LOC. Probably that's obvious. But we're going to use this in a side angle side situation and a side 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 situation. I'm going to put a little asterisk by the side 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 situation because there's something else that we need to do first in that situation before we jump into the law of cosines. So I'm just going to put a little asterisk there to remind me to make sure I talk about that when we get to that point. And then for law of sines, we'll do that if we have an angle-side angle situation, an angle-angle side situation, and then a side-side angle situation. And again, I'm going to put an asterisk on that side-side angle situation because that, again, is not as simple as just do the formula. So I've written down 5 things here, right? 5 situations. Which one of these stands out? Which one doesn't belong? Based on they're relating to angle congruence or similarity. It's not the angle-angle side. It's this side-side angle. And the reason that should stick out is there is no side-side angle. That's not a congruence theorem or similarity theorem. Let me demonstrate why real quick. I'm going to do this geometrically, so I'm going to kind of draw us a picture. Well, construct us a picture here, I guess. Make sure I pick the situation that I want here. All right, so let's say that we have this side that's 12 and oops, shoot, do that again. Let's say that this angle is 48. Shoot. One more time. And I'm going to make a line that goes through that. Okay. And then let's say that the other side is 10, right? Oops. So notice that there's 2 places where we can form a triangle, right? You could make the triangle ABC. Or you could make the triangle ABD. Everybody kind of see that? So again, you have a 10, a 12, and then a 48-degree angle. Or this one, you'd have a 10, a 12, and then the 48-degree angle. This is why there's no SSA congruence theorem, is because those 3 things being congruent doesn't guarantee you have the same triangle. They could be different triangles. That's one of the things that makes that particular situation the most difficult to deal with for us, is that sometimes you can get 0 triangles possible, 1 triangle possible, or 2 triangles possible. We'll look at that in more detail a little bit later, but that's a whole lesson in coping with that particular situation. Is everybody okay with seeing why that SSA situation is problematic, though? Okay. Did you do that drawing in your geometry class to demonstrate why there is no SSA theorem? No. Okay. That's okay. As an aside, there is a specific instance when that SSA theorem holds. And if that angle is a right angle, then it's true. Then that theorem holds. I think you guys have a special name for that in your geometry textbook. I think it's the hypotenuse leg. Does that sound familiar? That is the SSA theorem where the A is specifically has to be a right angle. So there is a special case where that does hold, but it's like hyper-specific. It's not any old angle. It must be right angles. All right. So let's look at an example here. Because we have about 10 minutes left, let's just do one kind of straight, or just, super easy. One example here. So let's say that A is 32 degrees, B is 73 degrees, and C is 13 degrees, or 13 inches. First thing that I would do is to draw a picture. Now, my picture is not going to be to scale. I don't give a lick about scale. So, Mr. Kulik, why do you need to draw a picture? Come on in. Yeah, no problem. The reason that I want to draw a picture here is because it's the easiest way for me to determine whether we're talking about an ASA or an SSA or a SAS or whatever situation. All right. So this is our picture, right? Everybody's cool with the picture we drawn? Which situation is this? Is this ASA or AAS?
ASA.
Very good, ASA. Why?
Because there's an angle, one side length, and another angle.
Yeah, so it's because the side length is an arm for both angles, right?
So does it have to be in between two angles then? Okay, you have to know the two angles.
It has to be an arm on both angles for it to be ASA.
Okay.
So for example, if we had angle, angle, and then side, that's what angle, side is going to look like, where the side B is an arm in only one of the two angles. Is that, you guys see the difference?
Yeah.
Okay. Now here, it's not so big of a deal because ASA and AAS are both law of sine situations, so it's not that big of a problem. But you certainly can't screw up SAS and SSA because those are two different, you'd want to use two different methods there. Okay. So we need to find angle C, we need to find side A, and we need side B. Everybody cool? Okay. Here, the order matters a little bit. Which one must I do first? Got to do angle C first. But that's good. It's trivial easy to do angle C. What do I have to do?
Add both of those guys.
Yeah. That gives me 75. Now, for the law of sines, right, that's sine A over A, sine B over B, sine C over C, I need a situation where I know both the angle and the opposite side. Which A, B, or C? Which is the situation where I know both the angle and the side? C. So I'm going to do sine C over side C. Okay. And then which should I do next? Yes, it is. Thank you. Does it matter? It doesn't. So we can do A. Sure. Oh, this angle A is 32. Why did I write that? And then we'll just cross multiply. So I have A times sine 75 is equal to 13 times sine 32. We'll divide both sides by sine 75. And then it's calculator time. And I'll use the fraction command to do this. So again, I don't have to worry about screwing up a parenthesis or something. So 713 is what I got there. Okay. Now to get side B, I can just do the Pythagorean theorem, right?
No.
No, why not?
Right triangle.
It's not a right triangle. What do I have to do?
You have to do the same thing.
Same thing I just did. Very good. So again, sine C over C is equal to sine B over B. Again, we'll cross multiply and then divide by sine 75. And I get 1287 there. Worth noting that if I do my little check, the smallest side is across from the smallest angle, the middle side is across from the middle angle, and the biggest side is across from the biggest angle. So I feel pretty good about this answer. Okay, we'll stop here. We'll pick up where we left off next time. No homework tonight because we haven't done enough to really have you guys do anything.